You get the answer to the question that you see on the screen. That's fine. Let's go to the next one. You don't have to write down the questions. I put it on the website. You can check it on the website where the course notes are there. Just below that one, tutorial on KEL, Kelvin's economy law. I put all the tutorial questions that you see on the screen are there, so you don't have to write the question or the tutorial problem down. You write only the solution. You number them according to the way they arrive here, or we are solving. Like the yesterday's one was number 1. Today's this one that you see is number 2. So read this question for a minute or two. I'll explain this problem first and then we'll go for the solution. Read this for 2 minutes max. Did you read it? So it says that the cost of conductor is Rand 1500A plus 100 per kilometer length of the line, and it's a AC 3-phase line. The small a is the cross-sectional area of the conductor, and it's in square millimeters. Right? After that, what is given? The rate of interest and depreciation, which is 10%. I'm putting my camera on so you can see. So it's 10%, and then the load is supplied for 75% of the year, meaning it's not on for whole year, meaning it's not on for 8,760 hours. It's 75% of 8,760 hours. The rate of energy, meaning the cost of energy, is given Rand 1.5 per unit. Resistivity of conductor material is also given 1.8 microohm centimeter, and we have to find out the most economic current density. It should be most economic current density, and the answer is given there. So we want to solve it. Now the cost of conductor, write down, as I say, for the solution. We don't know the length of the line here. So suppose the length of the line is 1 kilometer. Length of the line is 1 kilometer. Suppose the length of the line is 1 kilometer. Did you get it? So the cost of line is equal to Rand 150A plus 100 times 1, because it's 1 kilometer. So it's Rand 150A plus 100 times 1. That's the cost of line. That's the cost of line. Now the next step is to calculate the interest and depreciation. So the interest and depreciation is how much? It's 10%. So interest and depreciation on the cost of conductor is equal to that rand 150A plus 100 times 1, it was for 1 kilometer, times 0.1. So that's the cost of interest and depreciation on the conductor line. Did you get that one? Okay, it's fine. The next step is the power loss, calculation of power loss. So power loss is equal to 3 for 3-phase line, 3I squared. We don't know the current. So on the side you write, assume the RMS current is I ampere, capital I. Assume the RMS current is equal to I ampere. So 3I squared times R, resistance. Now resistance we are calculating from R is equal to rho L over A. Rho is 1.8 times 10 to the power minus 6. And A is in square millimeter. So rho 1.8 times 10 to the power minus 6 over A times 10 to the power 6. 10 to the power 6 is coming from kilometer to millimeter conversion. So 1.8 times 10 to the power minus 6 over A times 10 to the power 6. So that is R. And now the time is 8,760 times 0.75, which is at 75%. And now we need to consider the conversion to kilowatt hour, meaning times 10 to the power minus 3. Times 1.5 rand per kilowatt hour. So that is the cost of energy wasted. Cost of energy wasted is, now I'm repeating from the very beginning, cost of energy wasted 3I squared times 1.8 times 10 to the power minus 6 over A, that is R part, and 10 to the power 6 multiplied by 10 to the power 6 is becoming complete R now. Rho L over A. Rho is 1.8 10 to the power minus 6 over A times 10 to the power 6. Then the time, which is 8760 times 0.75 over 1000, which is 4, or 10 to the power minus 3, for converting it to kilowatt hour, and then kilowatt hour rate is 1.5 rand multiplied by 1.5 rand. So all these now is going to be equated with the cost of interest and depreciation. So write down below, according to Kelvin's economy law, according to Kelvin's economy law, the cost of energy wasted is equal to the cost of interest and depreciation. Cost of energy wasted is equal to the cost of interest and depreciation. Now energy wasted is equal to, on the following line you write 3I squared R, and then that whole equation up until you get to that 1.5 rand per unit, that number. So 1.3 I squared R times 1.8 into 10 to the power minus 6 over A times 10 to the power 6 times 8760 times 0.75 times 10 to the power minus 3 times 1.5 is equal to Now, from the cost of interest and depreciation, you taking only the part that has A in it. So it's 150A times 0.1. Did you get it? So from there, you calculate the value of I over A. Calculate the value of I over A, which is the most economic current density. Calculate the value of I over A, which is the most economic current density, and verify the answer is 0.53 ampere per millimeter squared, if you get that one or not. You must write down or tell me, write down on the chat box or tell me when you get this correct answer. Otherwise, we'll have to verify where you not getting it right. You need to let me know if you got the answer or not. I'm not getting any response from you, which means you are not there. That's what it is appearing to be like that to me. Can you respond? Nobody is responding. Hello? Just respond when you get the answer. If you did not get the answer, please let me know what is happening, what is wrong. The answer is there, 0.53. When you got the answer of 0.53 ampere per millimeter squared, please let me know. What is taking time now? It should not be taking more than a minute to get this number, get this answer 0.53. I over A, you need to calculate I over A from that equation, where you wrote 3I squared times 1 point times 10 to the power minus 6 over A times 10 to the power 6 times 8760 times 0.75 times 10 to the power minus 3 times 15 is equal to 150 times A times 0.1. So from that equation, you need to calculate the value of I over A. Can you respond, please, that if you got the answer or not? Is 3I squared R is the power loss. 3I squared R is the power loss. So 3 is 3 for 3 conductors, 3 phase line. I is for I because we don't know the current I, so we kept it I because we assumed it. I is rho L over A. Rho is 1.8 times 10 to the power minus 6. So that's rho. And L is 10 to the power 6 millimeter because it's in kilometer. And then A is A. So that's R. 3I squared R is the power. And then for energy loss, it will be the time that you multiply the power loss by. So it's 8760 times 0.75 because it's not 0.53. It's not 0.0. 0.53. Check, double check it. It's up to you. You can choose L. Fine, you can choose for 1 kilometer or 10 kilometer, 100 kilometer, does not matter. You will have the same answer. If you choose L kilometer, then L kilometer will come into the cost of interest and depreciation where we multiply. So it's per kilometer. So L kilometer, if you assume that it's L kilometer, your L will be there in the cost of interest and depreciation. And then if you choose L, that L kilometer will also come in the calculation of resistance rho L over A. So L kilometer will come there and L on either side will be cancelling each other. If you choose 1 kilometer, it will be the same thing. If you choose 10 kilometer, it will be the same thing. I did it intentionally, choosing L kilometer, choosing 1 kilometer, so that we can understand that it does not make any difference through a proper calculation and example. Is that okay? You can try it at home choosing L kilometer, or you can try it now as well choosing L kilometer. It won't make any difference.
Sorry, sir.
If you choose L kilometer, it will be for cost of interest and depreciation will be rand 150A plus 100 times L times 0.1. 0.1 is 14%. And then when you come for energy wastage cost, it will be 3I squared R. R means 1.8 into 10 to the power minus 6 over A. L times 10 to the power 6. L kilometer and kilometer is converted to millimeter. So L times 10 to the power 6 and then 0.75 for 75%, 8760 or times 10 to the power minus 3 times 1.5. So L is going to be cancelled out when you equate the following step.
Sorry, sir. Sorry. I have a question.
Is that clear now?
I have a question. Can you hear me, sir?
Did you get the answer? 0.53. Should not take so long, eh? I'm not listening. I'm not getting any answer from you yet. It's gone a long time. I won't be able to do more than one tutorial if it's going like this. We do at least 4 or 5 tutorial every day, 45 minutes, or at least 3. Can't go below 3. Can you respond, please? Hello. Either you keep your microphones or on, or you type on the chat box. If you're not responding, I cannot continue. Not going to help at all. It's 3I squared R. I didn't calculate that intermediate step here. Sumendran, I did not calculate that intermediate step. I took the equation and then you can find out what will be. I squared over 2A times. What is the point of calculating there and then calculating the following step? You can calculate that and get the correct answer. It's not that is something so difficult at third year level. Which equation I must repeat? Which equation can you which equation I must repeat? Kilowatt hour. Kilowatt hour is 3I squared R, cost of energy wasted. That's the equation for cost of energy wasted. Is 3I squared times 1.8 times 10 to the power minus 6 over A times 10 to the power 6 times 8760 times 0.75 times 10 to the power minus 3 times 1.5. That's the Paulus equation. And that is going to be equated with 158 times 0.1. And then you find I over A. $150A. What is written there? What? Sorry. Yes, 1500A. I'm sorry. Yeah, in that case, maybe the answer that 053 is correct. Check the answer and tell me 1500A. If it's 1500A. So 150, that will be 150. I was telling 158 all the time. I'm so sorry. So if it is 150, 1500A, it will be the answer will change probably. Let me just double check the answer on my calculator. Yeah, with 150 it will be 0.53 for sure. Check with 1500. Check with 1500 because I wrote 1500 in the problem. Yes, 1.679. That's the answer. So I need to change. Let me just do that change quickly in the answer because it was 150 in my. I wrote it 150. It was my mistake, and either the answer should change or that 150. So either 0.53 or 1.69. So that's the one. Can you go to the next one? I'll correct it and put it on the website. Everyone got it? You must confirm. I'm not getting any other response other than Umaira and Sumendran. And the other people have not confirmed it yet. Can you please? Can you please confirm, everyone? Okay, so I put those two different options. With 150A, you will get 0.53. If you have 1500A, meaning 1500A plus 100, then the answer will be 1.679. Right. So you can go to the next one. It's also a three-phase line. I'm reading it for you. After that, you will read it yourself, and then we'll start. So it's a three-phase line, 33 kV, 10 kilometer long. The length is given here now. We don't have to get confused. A 33 kV three-phase line, 10 kilometer long, and there is some loads that are changing now. 2500 kilovolt ampere for 8 hours, 2000 kilovolt ampere for 9 hours, 1500 kilovolt ampere for 7 hours, for 24 hours. So it's a daily load cycle. It's a daily load curve. 2500 kilovolt ampere for 8 hours, 2000 kilovolt ampere for 9 hours, 1500 kilovolt ampere for 7 hours. And then what else is given? Others are usual. Cost of conductor 7500 A plus 6000 per kilometer, and then cross-sectional area is in square centimeter. You must always look at that. The cross-sectional area and its unit is in square centimeter in this case. And then the interest and depreciation is given 8%. Cost of energy is 2.5 rand per kilowatt hour, and the line is in use for 250 days in a year. The resistance of the conductor material is given 0.173 ohm per kilometer per square centimeter. Now we have to determine the most economic cross-sectional area of the conductor. So read it yourself. Let me just rephrase these words so that it looks better. Right. So first step, we can calculate it easily. The cost of interest and depreciation. The first step is cost of interest and depreciation is equal to rand 7500A plus 6000 times 10 because it's 10 kilometer and interest rate is 8%, so 0.8. Is that okay? The cost of interest and depreciation rand 7500A plus 6000 times 10 for 10 kilometer and 0.8 for 8% interest and depreciation rate. In one step is done. Is that okay? Keep your microphone on if you can, so that we can hear it. It will be easy for us to communicate. Keep your microphone on. Is the cost of interest and depreciation that we're calculating in the first step. Cost of interest and depreciation. Cost of interest and depreciation is, it doesn't allow any changes or anything. Cost of interest and depreciation, it doesn't allow. Let me check. The cost of interest and depreciation, which is rand 7500A plus 6000 times 10 for 10 kilometer and 0.8 for 8% interest rate. Right? Got that one. The next step is to calculate the resistance of conductor. Do it in a step by step because you're missing it. Resistance of each conductor. Capital R is equal to rho L over A. So rho is given 0.173, it will be 0.173 for 10 kilometer, it will be multiplied by 10 and over A. So 0.173 times 10 over A ohm. That's the resistance of each conductor, capital R. Did you get that? You must tell me once you got it. R is equal to rho L over A. Rho is 0.173 and 10 for 10 kilometer, and A is going to stay as A. There is no change for A because that is the one that we are going to find out. Resistance of each conductor. Okay, so the next step is currents. Am I so fast?
Yes, you are fast.
R is equal to rho L over A. Suddenly, I'm not in grade R.
Sorry.
Third year. You need to be fast and you're studying electrical engineering. How long do you wait when you put your switch on and for the light to be giving you light, illumination? How long do you wait? Can you put your microphone on? You need to talk a little. Do you have a microphone? Or if you are not having microphone, type here. How long do you wait for the lights to give you illumination in your room or wherever when you put a switch on. How many seconds or how many minutes or how many months? 1 second. Why 1 second? I wanted to hear from Sanali Soe, who said I become too fast.
Prof. Prof, can you hear me?
I'm not too fast. When you are studying electrical engineering, you must know that electrical engineering is very fast. If we can be slow as we would want or as we would like, the system is going to collapse. The system doesn't give us time to respond if we don't want to respond. We cannot be slow. We have to be fast, very fast. We have to be very fast. If we are not fast, we need to prepare ourselves to be very fast. Once a light is on or once a light is switched on by a consumer on the generator side, if you are running the generator, you need to make sure that you respond to that change. Once a light is put off, you can respond to that change. Once a fault happens, a short circuit happens, you need to make sure that you can respond to that as soon as possible. You can't wait, okay, let me see, or I'll do it. No, those things don't work in electrical engineering at all. The time constants in electrical engineering is very, very small. If we don't respond, then things will be just destroyed and killing people, destroying all those things, all our appliances that are very, very expensive. We cannot afford to that. So I'm coming back to Umeshan's questions. Won't we convert the 10 kilometer to centimeter? We don't need that because you just go to that word, what is written here. Resistance of conductor material is 0.173 ohm per kilometer. So it's 4 kilometer already given, and that's why you can use directly 10 for 10 kilometer long line. Does it make sense?
Yes, sir.
If it was not, then we need to think what unit is there in the length of the line, what unit is there for the length of the line. Right, so each conductor. Now we're coming to the next step, which currents, this thing, I'm not getting the eraser. Okay, let me now go to the next step, is currents for, I don't want to make typographical mistake, currents for various loads. Now first one is I1. 3 different type of load conditions are there. The first one is 2005 kilovolt ampere for 8 hours. The second one is 2000 kilovolt ampere for 9 hours. The third one is 1500 kilovolt amperes for 7 hours. So we need to calculate 3 currents. So I1 is 2000 kVA by √3 divided by the voltage, line voltage 33. The first one is not 2000, sorry, it's 2500, 2000. So that's the current, kVA over the voltage, and the voltage is given as the line voltage 33 kV. So we need to take that √3 VLIL cos phi. Write down the formula on the side. I is equal to kVA over √3 VL. I is equal to √3 over sorry, I is equal to kVA over root 3. You can write it on the side. So you can find out this current and you find out the I2 and tell me what value. You find out the value of I3 and you tell me what it is for each of them. The same for I2 and I3, same formula we are going to use, but the kVAs are different, 2000 and 1500 for the next two. Tell me the answer of these three currents. 43, the first one. 43.73 is the second one. Quick, it should not take more than 10 seconds. You need to be fast. Electrical system is very fast. 35 ampere for the second current, and for the third current. What is equation of current? Could present what is happening with equation of current. It's written there. I is kVA over root 3 times the line voltage. I3 is 26.24. So we got the three currents. Next step is to calculate the power loss. Next step, I'm going now step by step because you're missing it. Power loss. Power loss is 3I square R. 3 times I squared times R. Right? Power loss is 3I squared R. And we don't have 1 R, we have 3 R's. So all those I's will go inside 1 I. So 3 times each current squared, that 43.73, 35, 26.24, those currents. But it will be easy for us if we go for energy loss instead of power loss. So I'm changing it to energy loss. So 3I squared R times T. So if I go for that, what it will be? It will be 3 times, the first one was 3.73 squared times 8 hours, because I squared and then time t is there, and the time is not the same for each of them, so it's different. 43 I squared times t. R will come later on. R is common to everyone. Then the second one, 35 squared times 9 hours. Then the third one, 26.24 squared times 7 hours. So all the currents and hours are gone now. Is that clear? 3I squared times t is gone for a day. The time t is for a day. And then the R will come as how much? 1.73 over A. Did you get that? It is R. Now we got 3I square R and the time for a day. Now for a day is done, but we need to go to 250 days a year. So we need to still multiply it by 250. Is that clear? $250 days for a year. So we're done for the year. When we are done for the year, we can go for converting it to kilowatt hour. So 10 to the power minus 3. So converting it to kilowatt hour, right? And when we're done with that, then we go for the energy rate, which is 2.5 kilowatt hour. So times 2.5. So now you can minimize this equation. Just number and a. Tell me the value. Is equal to what? Calculate this and give me the answer on the chat box. Write it down. Four zero 8.4. It can't be. It should have what a at the bottom. Check it. That is also not a correct answer to me. Anyone else with the answer? Yes, that's the answer. 101.02096 over a, and that is equal to that 7,500 times a times 10 times 0.8, which probably is giving 60,000 a. From there you calculate the value of a is equal to what? Why don't we convert the days to hours? It's already there. The hours are considered in the first place. "24 hours is considered in the first place. What we have here, 8 hours, 9 hours, 7 hours. So it's hours. And you multiply it by 250. So that's hours. To understand what is the unit here of the 7, 9, and 8. Yeah, 250 multiplied by 10 to the power minus 3 is for kilowatt hour conversion. That one is for kilowatt hour conversion. Because it's watt hour. I square R is watt hour. I square R is watt. And then you multiply it by hour, watt hour. And then convert it to kilowatt hour. That is 10 to the power minus 3. And then it's 250 days is converting how many hours. But the hours are there in the first place. So A is 1.297. Did you get that? Did you get 1.297, everyone? I see that Humaira has written there. Yes, he got it. So others need to confirm that one as well. Okay, Umesham got it. I need to hear from many others. Quickly, it should not take more than 20 seconds, 10 seconds from now. Anyone else got the answer? 1.297 or still something is wrong? I'm waiting, can't wait for long. And nobody has responded after Umeshan's response. Can you please confirm quickly? How do you get A? You equate this equation to 7500A times 10 times 0.8. That equation of energy, cost of energy, this is cost of energy. Sorry, this thing doesn't allow to correct easily. So you take that equation that is written there, that is cost of energy loss. It's not energy loss, it's cost of energy loss. That is cost of energy loss equated to 7500A times 10 times 0.8. No, 4.10 is wrong answer. Point 8 is the 8% rate of interest is given there. Rate of interest and depreciation. 10 is for 10 kilometer. Oh, sorry, why I said 0.8. Yeah, it should be 0.08. So you'll get the answer for this one. It doesn't allow to correct. Okay, let me just cancel these things. So you'll get the correct answer for this one. Thank you. Let's go to the next one. Next one is find out the most economic current density. Current density should be current density for a three-phase overlay line, which is in use of 2005 hours in a year. Cost of copper used for the line as material is 20 Rand per kg. Annual interest and depreciation is 12.5%. Density of copper is 8.89, and resistance per conductor per kilometer per square centimeter is given as 1.73 ohm. Cost of energy per unit is 16 cents. So we have to find out the most economic current density again. So read this question for a minute quickly. The most economic current density for a three-phase overhead line, which is in use for 2,500 hours. The cost of copper is given as 20 rand per kg, annual interest rate and depreciation given, density of copper is given, 8.89 gram per centimeter cubed, resistance per kilometer, and per square centimeter is given 1.73 ohm. Cost of energy per unit is 16 cents. So we have to find out the economic current density. Now many things are not given here. We don't know the even a cross-sectional area, which was mentioned in all other problems, while it was showing the cost of conductor. A was there. In this case, A is not there. So we assume, write down, suppose cross-sectional area is A square centimeter. First step is assume square centimeter. And we also don't know the length. Length we need to assume. You can assume L. It's lowercase l or capital. Let me write capital L because it looks like I. L. Same unit we're choosing. We don't want to complicate it with different units, kilometers, and we still have to then convert and make it complicated. Length is assumed to be L centimeter, and then we need to choose the current as well because the current is not given. So we assume that it's I ampere. It's capital I ampere, right? So once we are done with that, did you write it? We assume these three things first. Then we can go for calculation of resistance of each conductor. R is equal to rho L over A. So it will be 0.173 times L centimeter divided by the A, which is cross-section rho L over A, so that is that A, and in the unit it is in per kilometer, but we are using centimeter, so we have to convert that to centimeter. It will be 10 to the power 5 here. Does it make sense? Resistance of each conductor. How do we calculate resistance? Is rho L over A. Rho L over A. Rho is there, so we took L. That's fine. But L we chose to be in centimeter, whereas in the problem what is given is per kilometer. So that L is now converted in kilometer. So L over 10 to the power 5 is now in kilometer. Sorry, in centimeter now. In kilometer here, so it's kilometer, and then centimeter remains that same. Check it. So it will be 1.73 times 10 to the power minus 6. Ah, goodness. What happened? It doesn't allow. It got deleted or what? Let me write down again. So R will be 1.73 times over A. Did you get that? If you got that one, then we can go for calculation of cost of energy loss per annum. So what it will be? It will be equal to P times I squared, Pi square R. R is 1.73 times 10 to the power minus 6 over A. So that's 3I square R. Sorry, L should be there. I missed that L. 1.7. Sorry, these things causing. Let me just remove them. Cost of energy wastage is equal to 3. Let me write down in the following line. 3 times I squared times R. R is 1.73 times 10 to the power minus 6 L over A. 3I square R. Now we need to get the time. Time is 2500 hours. So 2500 hours. And then again we come to convert it to 10 to the power minus 6 because it was 0.173 and I chose 1.73. If you choose 0.173, then it will be 10 to the power minus 5. Is that clear now? So I'm converting it to kilowatt hours minus 10 to the power minus 3, and then the rate is 16 cents, meaning 16 over 100. Is that okay? So that is equal to what now? Tell me the value of this one. What you getting for this equation when you simplify this? When you simplifying this one, what you getting? Can you let me know this one? So you can verify if you got the right one. Okay. Let me know quickly. Yes, that's the answer. I squared over A. L should be there. L is missing.
Yes, ma'am.
No, something is wrong. That 2 times 2.076 times 10 to the power minus 6 it should be at the numerator.
Oh, yes, I'm correct that page.
It should be at the numerator. And L is missing. It should be I squared L I squared is missing. Where is I squared? I squared is missing. For Caesar's equation, I squared is missing. Otherwise, it's correct. I should be I squared. Yes, I squared L 2.076 times 10 to the power minus 6 over A. At the denominator, only A is there. So we can go to the next step to calculate the volume of conductor. Now want to calculate how much volume of copper required. How much is 3-phase lines, so 3 conductors for 3-phase lines. We need considering the neutral here, you must remember that. So 3-phase line, 3 conductors, neutral is made up of another, and in deep transmission lines we don't have that, but we have an earth, that is separate issue. But in these cases we are going to use 3 for 3 lines. So 3 for 3-phase lines, and A is the cross-sectional area in centimeter. So that's 3A, and L, length of the line. So it's L, and that is in centimeter cubed. Right? Now we can calculate the weight of copper required. So weight will be calculated by volume times density. So what's its value? You tell me. Did you get the volume? Did you get the weight? Once you have the volume, then cost of copper. Rand per kg is given. You can calculate the cost of copper. Once you have that, you can calculate the interest and depreciation. The interest rate is given as 12.5%. So what's the final answer for this interest and depreciation on the cost of contractor? What's the answer for the cost of interest and depreciation? Interest and depreciation, giving the final one for interest and depreciation. Is final interest and depreciation is 0.066. AL is missing in your answer. 0.066 AL should be there. Am I right? It's 0.066 AL should be there as multiplied. Did everyone get it? 0.066 AL. Okay. If you have another class, it's fine. Now, just to let you know, you must that this 0.066 AL will be now equal to that equation 2.076 that one, and then you find I over A. So 0.66 AL is now going to be equal to that 2.076 10 to the power minus 6 times I squared L over A, and then you find the value of I over A. So that's what you are going to find out, I over A at the end, and the answer is given there, 1.79. Okay, thank you very much, Coil.